Okay, let's analyze the following operational circuit called the non-inverting op-amp, in which we have a input Vs connected to Vp. Now we note our ideal characteristics as a reminder. Let me write that down. Ideal op-amp So here's our ideal op-amp, in which we have Vp is equal to Vn, Ip equals In equals 0. And I discussed that in an earlier video. So let's take a look at this. Vp equals Vn. Well, what's Vp equal to? Well, we see Vp is connected to Vs. And we know that Vp is connected to Vn. Now what's Vn connected to? It's connected at this point right here. Now we note also that the current In is equal to 0, so all of the current flowing through R2 also flows through R1. Therefore, R2 and R1 can be approximated such that they are connected in series. So we can use a voltage divider associated with this part of the circuit. That is, we can redraw the output part where we have VO. Connected to VO is R2. At the other end of R2 is R1. But at this point right here is Vn. So Vn, we can use a voltage divider, and that's equal to R1 over R1 plus R2 times our output voltage VO. So we can replace Vn as follows, shown here: R1 plus R2 at the denominator times VO. So therefore, our input is Vp, which is equal to Vs. So in terms of our output, Vs is equal to R1 divided by R1 plus R2 times VO. But that implies that VO is equal to R1 plus R2 divided by R1 times Vs. Well, R1 over R1 is 1 plus R2 over R1 divided by Vs. Okay, so that's our resulting output in terms of our input Vs right here, and it's just a function of our external resistors R2 and R1. R2 and R1, and we can adjust the gain as long as it's below plus or minus VCC, because that's where our output voltage is limited to. So that's how we do our analysis of our operational amplifier, and for this one it's a non-inverting amplifier. And what I mean by that, if I have an input that looks like this at my input, then I have just a bigger input that's in phase. This starts at 0 and this starts at 0. If it's a non-inverting, which we'll see next, it would look like this, opposite. Alright, so for this one it's a non-inverting op-amp. We use the ideal characteristics of Vp equal Vn, and Ip is equal to In equals 0, and we use that approximation so we can use a voltage divider at our output circuit. And then we can, at our input, is related to our output in terms of using Vp equals Vn. So once again, our gain is governed by our external resistors R2 plus over R1, and then we add a 1 to it. Now let's say we want to design this op-amp to have a gain of 10. So here, this part of the equation, we want to have a gain of K equal to 10. So 10 is equal to R1 plus R2 over R1. Well, then this implies that R2 over R1 should have a gain of 9 right here, or a ratio of 9. Therefore, we can say R2, let's say, is equal to 90K, or 90 kilo ohms, and R1 is equal to 10 kilo ohms. So that's it with this design. So let me make a few comments about the problem of choosing resistor values in op-amp circuits. See, although the values of some resistors occur from a few ohms to several hundred ohms that are commercially available, we usually limit ourselves to the range of 1 kilo ohm to 1 mega ohms. The lower limit of 1 kilo ohm is imposed in part because of power dissipation in the resistors. Typically, we use resistors with 1/4 watt power rating or less, and that the maximum voltage in an op-amp is often around 15 volts. As a result, the smallest 1/4 watt resistor we can use is around 900 ohms, or 1 kilo ohm. The upper bound of 1 kilo ohm, mega ohm, comes about because surface leakage makes it difficult to maintain the tolerance in a high value resistance. Also, high value resistors are also noisy, which leads to problems when they are connected to the feedback path. Hence, the 1 kilo ohm to 1 mega ohm range should be used as a guideline and not a strict design rule. Actual design choices are influenced by system-specific factors and changes in technology.